Okay, so as you noticed from the notes, for those of you who checked the notes, I just exchanged material, and in the presentation I've been consistent though with the program outline at the beginning. So I left the question of linking and other concepts related to helicity at the very end. I want to go on with this M of H. Remember yesterday we had emphasis on M of H. M of H is basically, given the fact that flux and volume are conserved, is basically the information we need in order to find the minimum energy states. And we expect that H, being a measure of the twist, internal twist of the field lines, we expect that probably M of H has to be, for the minimum, is probably a function with a minimum in H. And so we are looking for H equals 0 if we want to have really the minimum of that. Now, there are particular results. One has been, has received contribution from many people. I have to quote a number of them that worked. The first is rooted in the result of Arnold. So there are a number of people that during different years worked on this. 1974 started, and then there is an important contribution by Friedman, Michael Friedman. He was a Fields medalist and is still working on topological aspects, but on quantum entanglement. Actually was responsible for the theory division of Microsoft up to some years ago. Friedman and Hay. This is a result of 91. Then I mentioned the result of Moffat, 1990. And I also contributed, and this is the result I'm going to show you very briefly. This is 2008. And the result is the following. So this is a compendium of all these contributions. Let B, say, the field in a tubular knot. So this is a magnetic knot. B, a zero framed link in general, or not. It doesn't matter. We can say link. A link is just a collection of knots under volume, or let's say signature preserving flow. We have the following. In general, first is that magnetic energy M of T is greater or equal to Q divided by, so is a constant, Q divided by pi, and the volume, this is a constant, the volume is conserved, to one third times the helicity, magnetic helicity of the field, of the system. Yesterday we saw that under relaxation, magnetic energy was bounded from below by a quantity Q related to this Poincaré inequality times helicity. And Q was a measure of size. We wrote Q of the order of 1 over L. And indeed, here we have the cubic root of V at the denominator, which is indeed a measure of the length of the system. So indeed this Q can be identified by this quantity. And the second information was M min. M min, we had this M function left dimensionless function left undetermined, and we can now say that this is pi v a third times phi squared times C min. So the m, the little m, if we set h equals 0, his function is a topological crossing number. So it seems that this result is kind of closing the door to this discussion, but the story starts from here. Why? Because, now I didn't write it down, maybe I have it somewhere. C min, if C min is 3, we cannot go under 3, then we have only one knot type. But if C min grows for 1 knot type. But for 5, we have already 2 knot types. And for 7, many more knot types. Many more. And this C min grows the knot types, so the number of knot types topologically different, let's say that goes with a constant a to C min. Increases with C min, you see, very rapidly. So the question of having, suppose we take a 5 crossing knot, a knot, here there are 2 knot types, and here it says that the minimum energy is due to C min and is this. So, what does it mean? If we have 2 knot types, we put a 5 here, and M min, are we sure that M min is the same for the 2 knot types? You know, there is an information on the volume that doesn't help. So, even if we fix volume for the same knot types, we are not quite sure. And the reason is that this information is correct, but is valid, how to say, on average. Suppose you take C min equal 10. You have so many knot types. How can you have a function so precise that tells you for every single knot type maybe tiny differences in energy? So that's why in the notes you have this rather elaborated calculation of the Lorentz force for the meridional and the axial field inside the tube, because we need to have some information about the twist and then set the twist eventually to 0 and maybe examine all possible knot types through some method to see if if we can recover this, and if the information that we get not only allows us to recover this on average, but tells us something about each single knot type. So now this is a work that is mentioned there, but it's too long to reproduce, and is based on constraint relaxation of knot types, of magnetic knots. And the constraints are the assumptions I'm going to write. So this is the result of work that I've done with Francesca Maggioni, and myself, and is 2009, I think, and is also based on earlier work done by Chewy and Moffat. This one I don't remember, though, I'm sorry. Some time passed, and I didn't, it probably is in the notes. Has to be, I have no idea. I think is maybe 1992, something like this. Sorry. Probably I've written that surely in my papers, but I don't have the exact reference at hand. Anyway, so they elaborated the application of through the application of calculus of variation, a relaxation under the assumption that twist H may change. We did this work with, let's say, a choice of Mercier coordinates that ensure that they are orthonormal. And so we found basically the same results because it gets rather sophisticated, so no much difference between the two approaches, but it's important to state the assumption, the constraints. So the result is the following. Let Bk denote these magnetic knot or knots under given by the decomposition B, Bm plus Ba that I mentioned last time, minimization of magnetic energy of M of T is subject to the following assumption. Let's call them constraints, because to do some analytical work you need some simplicity, and in numerics you can implement things to improve this result, I'm sure. So first of all, this is invariant, and we know that. The second assumption is that flux tube cross section remains circular. At all times. And in particular at the time of when the relaxation comes to an end. This is a rather strong assumption because it's a fluid. And so it will relax and relax and relax so that its cross-section will deform and adapt the tightening process. So not at all good assumption, but in order to make some progress, this is the chance we have. Then there is a perturbation. This is long to explain, but there is a flux perturbation. There is an average flux plus some sinusoidal perturbation. So this is independent, is uniform, let's say. If we understand what we mean, is this fluctuation is uniform along the flux tube, And then the last one, the knot length, each knot length is assumed to be independent from H. When you put twist in a rope, of course, it eats up some length. So you assume that H and total length are not talking to each other. Then, under this assumption, we have that M star, which is the minimum under these constraints. So I put a star to remember, to tell us, okay, maybe it can be relaxed even more. But anyway, this is the formula. I will write the formula in a moment. I will explain in a moment this formula, but let me write it first. Lambda 4 third over 2 pi to the 2 third plus pi 4 third h, that h squared over lambda to the 2 third times phi squared volume minus a third, where lambda is rope length. I'll tell you what is rope length. Well, rope length, there are more precise ways to define it, but imagine that we go to the minimum, the relaxed state, then rope length is a non-dimensional quantity that refers to the ratio, I got very often confused which way this ratio is defined. Don't tell me that I missed it. Maybe I did. No, I didn't. L over R, because sometimes I think of R over L in many contexts. R over L, is the aspect ratio, so that's why I got confused sometimes. L star is the minimum length under relaxation of the knot, and R is the maximum, remember, the flux is conserved, is the maximum radial dimension of the tube. So when the tube gets fatter and fatter, remember the torus. We start with a simple unknotted torus, and we relax it to what we may say is a torus without a hole. Something like this. You understand what I mean. Now, suppose that this cross-section is circular, then this is R, and in particular R star, if we keep it circular. Then I didn't draw circles just to tell you that, of course, nobody nature does not prescribe to stay circular. So it can squeeze and squeeze and squeeze, right? But suppose we stay circular, and if we stay circular, then the radius of the tight configuration, tight knot, and this is loose knot. In particular, this is the unknot, okay? Right. I'm playing with words a little bit. So this is the loose knot, and this is the tight knot, and the tight knot will have a L, a total length in the tight configuration, which is minimal, and we take the minimal length divided by the maximal radius, and we define rope length. So rope length is a number, and actually is a very powerful number. And you understand that is useful. You understand because, you may take ropes, and you tighten the knot, and then the rope, if it is a physical thick rope, then hardly changes its cross-section. But with this measure, you have some ways to analyze or to measure properties, mechanical properties of this knotted rope. Why I'm saying this? Because if you ask a sailor, or if you ask a mountaineer, they know very well which knot to use in order to have a certain amount of, in relation to the function of the knot. For example, in mountains, you climb and you knot the rope in order to save your life, to insure yourself, but then you have to knot the rope in a way to be able to unknot it quickly. So you knot a particular type of knot that is easy to be unknotted. So you don't do trefoil knots. Because when they are tight, especially if you fall, you know, they get extremely tight, and you cannot unknot them quickly. So the properties of knots are very important for lots of reasons. And in nature, these properties are reflected. Because not all knots are used according to, according to the function they have. If they just have to hold it, okay. But if you think to undo it, then you have to. And so this is related, of course, to the material surfaces of the knot that touch themselves, and the friction that there is, because these are real ropes, real knots, etc., etc. So there is a very, very interesting field of study. Anyway, so this is the parameter. A brief comment, and then I want just to show you two curves, and we are done about this part, is that indeed the twist is here. If it increases, twist increases the minimum energy. And so if we are looking for m, little m over there, m at h equals 0, which is the state of these results, in a sense, then we have to neglect this functional dependence. Okay? But, of course, you can trace, you can draw your diagrams and see how this changes, and this was done. Now, let's assume, for simplicity, that h is 0. So the internal linking is 0. So we are left with this function. We are left with this function. And now what we do? Now we do the following. You know, is a function of lambda only. And lambda is, oh, sorry, I forgot to say it, is rope length. Rope length. Now, in order to find this for knots, for all possible knots, well, this is a big work. So we resort, there's a group of people who have done wonderful, wonderful work for a number of years. So first of all, let me say something about this knot tabulation. So nowadays there are websites where you can go and check various invariant quantities, topological invariants, and the geometric information sometimes on knots. And so one website is one of the many. One important website is Knot Atlas, for instance. This is the work of a number of people, I think originated from Barnatan Initiative and then developed. So you check on this atlas of knots and you have many, many properties. And then people started to say, okay, what about relaxing the knot? So relaxing the knot, you do it numerically. You take every single knot, and these tabulated, maybe there are, I don't know exactly, but suppose there are hundreds, maybe thousands of knots, of different knot types. So you take information from the atlas of knots, and then you construct a code, a numerical code, that relaxes the knot under the assumption of volume and flux preserving. Now, we can drop the flux, but the volume, so if it shrinks, it increases in the cross-section. Flux is a field through the cross-section. So the flux is, in a sense, can be worked out for physical application. But in the numerical code, we want just to establish this pure number. This is a pure number. And so in order to establish this pure number, we want to have a code that relaxes this knot to the tight configuration. So you give a knot, say the trefoil knot, you get it fatter, as I showed you yesterday, and then you get your information about lambda. You compute L, you compute R, and you have your lambda. So there is a table. So this work was done by the group, a number of people. I would like to quote Cantarella in particular, and Eric Rodon. I would like to also quote another person who contributed so much to this is Rob Sharine. The inventor of a wonderful program, NotPlot. Maybe I'll show you just a snapshot of NotPlot. NotPlot has knots in it, and till some years ago was free. Now it costs, well, it's really little money, even for China. It costs something like $30, something like that. The knot plot was developed a long time ago now, and so it takes a knot data, and with this data you can work out lots of aspects. Also geometry of knots, because these knots can be deformed. Given a knot, you deform it without cuts. Or you can construct new knots from scratch. Or you can construct something that you think is a new knot, and then you let it relax. And during relaxation, through a number of forces, one being the elasticity, the other one may be the magnetic, and the other one, you find out if the knot that you invented is known or not. It's a way to explore new knot types and other properties. Cantarell and Rodon developed a program that is called the Ridge Runner, and we relied, so Ridge Runner, I'm sure all the data from Ridge Runner are freely available, lots of data. So you checked on hundreds of knots, and now the result I like to tell you is this. So we took Ridge Runner data, and we put them here, and we just plot the energy, that's all. And we found something quite remarkable. So remember, we are talking about tight knots, so we are at the ground state of that energy. Ground state of that energy. And so we have found something like this. You have it in your notes. So under Ridge Runner relaxation, you have a best fit. Here we have a sort of non-dimensional energy. We non-dimensionalize this number. From M we go to little m, and from little m we divide it by the Titan knot. So this is a function of the knot tabulation. But which knot tabulation? That was the new thing. So we tried to put here the knot as they are tabulated till recently. And we didn't find any particular, emerging behavior. But then we had the idea to have a look at Ridge Runner data and to tabulate these knots according to increasing value of lambda, of rope length. And if you put here your knot types organized with respect to rope length, then the story is different. I want to tell you, knot tabulation. You go to these tables of knots. I told you, for 5 crossing, you have 2 knots, 5-1 and 5-2. For 6 crossing, 3 knots. Sorry, I forgot to say. I jumped to 7. 6 crossing, you have three types of knots, and so on. Why the first knot in the 5 crossing class is first, and why the second knot is second? And for years, I thought, you don't think about this. There may be some reason. And then when you want to use and you want to put order here, you have a 5-1 and 5-2. You put first the 5-1 and second the 5-2. But then you realize that there is no reason to have what we call 5-1 before the 5-2. You know what is the reason? Historical. The 5-1 was found before and the 5-2 after. That's why. So when you go to 7 crossing, 8 crossing, 9 crossing, you have so many knot types. There is no reason why a given knot has to be there or after the other one. But if you order this knot according to rope length, then it's a different story. And the diagram you get is something like this. And this curve obeys this law. So these are ordered according to rope length, according to lambda value. So the function is an empirical one, is 4.5 logarithm of this number, the position of the knot, plus 10.5, and this result is 4 knots. How many? We have 250 knots. 250 knots have been computed using Ridge Runner. And when we go to links, I would put an L here, we have this 4.5 logarithm of the position of the link according to rope length plus 9.3. Two things. First, the shape of this curve. Is not amazing? The one family, 300, 250 knots fall more or less on this curve, and the links basically on the same curve. I mean the shape. I don't want to talk about this. I want to not numbers. Don't focus on numbers. Focus on the shape. Shape is interesting. Shape is interesting. So I don't want to say anything. I just ask students and young people to tell me, do you know this? This is a function. You have to think. 200 is nothing. So you think of thousands of possibilities, and so it has to be interpreted in a sense of statistical mechanics. This is like related to Boltzmann statistics, I don't know, something like that. Right. And the second thing is the remarkable, I mean, we didn't force anything, it's just the remarkable similarities between these two laws. I mean, this is basically, is a best fit, this curve, of course, because don't think, I mean, this is numeric, right? So it's a best fit law, and I reported the accuracy of this best fit, etc., just to let you understand how well is fitted by these functions. And this number is exactly the same, and this is a very small discrepancy. You may think of alter a little bit according to some ground state energy, All right, so this is the part, and then there is further discussion because there is an attempt to justify this behavior, but I don't want to dwell on that. You can read it for yourself. I want to move to helicity now, because so far we discussed about the relevance of crossing numbers. Each knot has a crossing number, but here there are knots with the same crossing number. There are different knot types with different energies. And if you do an average on each family, you recover the expression I told you before, function of C mean independent of the knot type. So you recover that. All right. Now, I'd like to mention, since I mentioned the group of Cantarella, I'd like to mention that there's been work on, the last 10 years, less than that, works, Cantarella, Rodon, and the people in high energy physics to establish a correspondence between fundamental state of matter in terms of energy and this information on tight knots, etc. In particular, I'd like to mention work by Tom Kephart. So if you want to pay attention, Tom Kephart and Roman Bugni. I'm in trouble to remember how to write this. I think it's like this. So they, together with Cantrell and Rodo, have a paper on, and probably more than one paper, on a big paper I remember, on establishing a relationship between the tight knot in the ideal relaxed case and the measurements from CERN, from high energy physics. All right. Helicity now. Let's go back to helicity and its topological interpretation, because we mentioned that the minimum energy is bounded from below by helicity, and also the energy is a function of topology, especially when we go to, the minimum energy, certainly a function of topology. So what about helicity as a measure of topology? So this is basically rooted in work of Moffat 69. I've thought to propose you first a measure of topology, so we understand what we talk about, because we know what is helicity, but topology has many invariant quantities, and one is very important, is due to Gauss, 1833, and then he disappeared, the result, because it was a result he wrote for himself on a personal notebook. And then these pages went lost, and they were found in 1867. And in 1867, still this result didn't circulate much, because it was collected with the new material found of Gauss and was put in a collection of course, many other results, and they didn't know where to put this result, because this result has to do with topology, but topology emerged at the time of Gauss, so a few years later, there was no topology. No topology. I told you, topology is the word invented by Listing to a student, probably the only real student of Gauss. People say Riemann was a student of Gauss. It is not true. Gauss was chairman of the committee who appointed Riemann. But Listing was a student of Gauss, and Listing invented what we attribute now to Möbius. Invented the Möbius band. The Möbius band is due to Listing. But Listing in topology didn't do very much. There's a little booklet. We examined the booklet with Claude Weber, who is an expert on these things, and he told me we agreed that there was not much in that. Anyway, he introduced the word topology. The Latin word was geometry of position. So I told you, in Maxwell, if you look for topology, you don't find any. So Renzo, what Renzo said to look at Maxwell preface, look for geometry of position. Geometry of position, the whole chapter. Okay, so Gauss remarked, and the mystery remained on how he proved it, because there is no proof, that this quantity, let me call it a linking number, let's say linking number between two curves, closed curves, etc., etc. Two simple closed curves in R3. C1 and C2 is given by this formula, LK12, 1 over 4 pi, double integral on C1 and C2. These are, of course, closed integrals, x1 minus x2 divided by, dx is a triple product, dx1 cross dx2 divided by x1 minus x2 mod cube. A topological invariant of the link between C1 and C2. And the story behind this is interesting, very interesting. I wrote a paper on this with Nipoti, and if you like to have a look, I think is nipoti, in 2011, stimulated by so many attempts that people made to justify this formula, because, and we reconstructed this formula from the work of Gauss, reading work of Gauss, because many people report how he derived possibly this formula, and is absolutely impossible. He did it on the basis of what people claim. But if you go to Gauss' work and you study, for example, his work on geomagnetism, then you understand how he gets to this formula. Now I'll try to justify it quickly for you, because the formula that you see here is exactly the formula that is written on his private note. So if you look at this formula this way, you are puzzled, right? Because you think, how on earth, he says that this double integral of a curve and another one of, say, this one and this one, linking one with the other, say C1 with C2, is a quantity Lk that is a topological invariant of the link. You wonder how on earth he could say something like this. And I've read incredible attempts. The most stupid ones are the ones that say, okay, I prescribe the geometry of C1 and C2, say 2 circles, and I compute this thing. Can you imagine? I compute these things analytically, and then in some way, I justify that what I get, a number, is invariant under deformation. Or even worse than this, I give some parametric prescription of this. Impossible. I mean, through geometry, you want to prove something about topology? I mean, is possible. We know that there are a couple of instances where it's possible, but is extremely, I mean. One other possibility is to interpret maybe what he did. So my interpretation to you in a minute is a bit rough, but please follow me. First of all, there is a 4 pi here, and is there. So first thing is to remove this 4 pi here and put it inside. 4 pi. It's good to have it there. And then you have x1 minus x2, x1 denoting a point on C1, x2 denoting a point on C2, right? And so you do, there is an x1 minus x2. Let me call x1 minus x2, let me call it R, okay? Is a vector. And this vector, so we do the following now. We have a vector here, R, and the vector here, like this. And then we notice that R divided by mod R is a unit vector, right? So I simplify one R here, I put a hat, and I have this, right? Okay? Nothing changed. And then we do another little exercise, and we think that this R, this one, is a unit quantity. So this quantity is a unit quantity. And if it is a unit quantity, this is just 4 pi. It's just 4 pi. And now we do one more thing. We didn't do any calculation, right? We just observe things and learn from elaboration. Now we notice this is a triple product of the quantity here is a unit, no dimensions, and the dimensions here is just a surface. dx is a length on a curve and another length of another curve. So this is a surface. This is a surface with its own normal direction. And this is a particular surface. Do you remember? Yeah. Okay, it's a sphere. And now I cannot pretend to convince you because you have to read. It's a history. It's a piece of, work. But let me just tell you that first, Gauss was a royal astronomer. His main business was about astronomy. Secondly, that he so often thought of himself in the sense of us, as the center of the observation. And observing the sky, he was at the center of a sphere. And indeed, when you map whatever is in the universe, you map it on a Gauss sphere. And that is the Gauss horizon. So now, you think to be at the center of a sphere, and you look at these curves, and you interpret these curves. Gauss, I claim that he came to this through potential theory. And you can read all his contributions. He got this formula from geomagnetism, from potential theory. But there is another possible interpretation, and this is the interpretation that these curves are trajectories in celestial mechanics. And you wonder, don't think of a linkage, think of orbits. And you wonder, one orbit is like this and the other is like this, totally unlinked. And then maybe they are parallel, maybe they intersect, one orbit against the other. And then if you just do a further move, you have one orbit that is inside the other. So if you are at the center of the sphere, you can see the apparent crossing, or the real crossing, if there is a collision, satellites, etc. You see an apparent crossing of these orbits. So this ratio gives you the possibility of counting the apparent crossings of the strands, of these strands. So you go from this part to the solid angle definition. This is an elementary solid angle, and the integral of this is, because it's topology, it does not depend on the geometry. You can reduce all this to something like this. Sorry. This is solid elementary solid angle. And counting the apparent crossings, you can reduce this formula to an algebraic expression. You count the crossings. So I say, well, there is an 1/2 for some reason, summation over the crossings. Now I need a quick way to let you calculate that. So algebraic interpretation of linking. Okay, this is simple. We have to introduce a notation, first of all. Notation is, for example, this one. This is, you assign the sign minus to this, say -1. And I usually put my thumb, everyone has his own rule. But suppose we stick to the same rule, is to put a thumb on whatever is above. And whatever is behind, under crossing, if it is against your fingers, is a minus. And if it is in favor of your fingers, you put a thumb on the top one and you have a plus. Okay? So all the time you have a plus and the minus, you have a crossings. All the times you have a crossing, you have a plus or a minus. Okay? You call this quantity plus -1 is the sign of the crossing. And then what you do, you take your link. You take your link and you project it on a diagram. And now I know what you're thinking, because you're thinking, oh, well, it depends on the projection. I can project it this way or the other way, etc., etc. Yes, it's true. It depends on the projection, but that number, this one, i.e. this one, i.e. this, is a topological quantity. It does not depend on the projection. Once you get the value, whatever is the deformation, whatever is your angle of your line of sight, your direction of projection, whatever it is, it doesn't change. So let's put an orientation of these curves. We like oriented curves. Why? Because we think of fields. Fields have an orientation. So we like to think of these curves as oriented curves. Which orientation? Whatever we like. We like this one? Okay, we put this one. Okay, we can change orientation. Doesn't matter. It will affect the computation. I don't know. We'll see. Okay, so, and then we have to use this rule. So I have, just to start, good idea to put arrows near each crossing consistently. And so here I have to go like this, etc., etc. And then I put my rule, and my rule says that this is a plus one, and this is a plus one, right? So I go here, and I compute for this system LK1, 2. I have a plus 1, and plus 1 is plus 2, and divided by 2, a half, plus 2, plus 1. Okay, so I'm happy. I can compute the linking number between these two curves, whatever is their orientation, and I conclude that linking number between these two guys, 1 and 2, is 0. I'm very happy, right? Because it works. I can compute linking number of whatever linkage I like, and I'm happy. So is a topological quantity, does not depend on the projection. I jump immediately to something of these days. So it's very good for computations. Fantastic. You take any network of curves, you take a projection, any projection, possibly the simplest, possibly the most convenient, whatever, any projection at one instant, and if topology does not change, you apply this rule, whatever is the complication, you get the number that is a topological quantity.
Can we use the origin formula to calculate this linking number?
Yes, you can. Of course you can. That formula has lots of troubles for certain guys that are quite experienced here in numerics, because you see, of course you can, yes. But you have to do, to integrate on each curve, and then you have a trouble of this elementary contribution when the curves are very close, and then you have 1 over the distance x1 minus x2. So the further problem is when these two curves are extremely close. So it gives you a lot of trouble. But of course, it's done. I'm tempted to say why has been done so much. I shut up. You will see why has been done already many times without knowing that they were using linking number, but I'll come in a minute to that. Okay, so Maxwell, yes?
Before the next step,
yeah?
may I just show you, I have uploaded the paper, your paper. Gauss linking number revision.
Okay. Okay, thank you, thank you. It's an interesting paper, not because I wrote the paper. No. It's a lot of work, but it's beautiful. I think I'm very happy about that paper. Absolutely. It's one of the things that do not affect science at all, but it's one of the things that you are relieved. You see very well all this development of various ideas. Anyway, and Maxwell, from that paper, I put a copy of what I found, because I wanted the Library of Cambridge at doing a lot of search one summer. Maxwell noticed, first of all, he derived himself the same formula, but independently. And when it was time for his book to come out, it was a bit late for the formula, because the formula of Gauss was made known to people in 1867, which is exactly the time that Maxwell was ready to publish the formula. And so Maxwell, as great he was, he acknowledged Gauss. And he immediately addressed the attention of Tate. Remember, Tate was his former tutor, good friends, schoolmates. He addressed the attention of Tate that in Cambridge Library there is a copy of the Gauss linking number formula made public. And so he said, I had to search for it. He used a different word, but I had to search for it a lot, because of course it was a rare publication to have, and they could read German, by the way. At the time, people used to read, to speak at least one other language. They were writing. He was writing. They used to write. If I were writing to you, I would have written my letter in Chinese, and you would have replied in Italian. You know, amazing, different times. To be gentle one another, you know, to be nice one another, and so they could read German. Anyway, and he noticed instantly that this formula has a problem. There are some knots or some links that do have a problem with this formula. And Tate was so happy. You remember the ups and downs of knot topologists. It was a time where already collected some material, ready to publish it, but it was hit by this information by Maxwell. And this information is in the book, in his Electricity and Magnetism book. So you have to go second volume, and you have to search a little bit for that. It depends on the edition. I remember the edition I remember was about page 70 or something like that. And you look for linking number formula, you look for solid angle. Solid angle, that's the entry, the best entry. And you immediately find a section dedicated to solid angle, and then you have the formula immediately afterwards, and is the way he derives the linking number formula. Amazing. It's a theory, a mathematical theory of electricity and magnetism, volume 2 of Maxwell. It's a standard book, but many miss that. And when I was young, I started to tell people, well, you know, there is a particular type of knot and link reference where he says that linking number fails. So he immediately noticed that. As soon as he derived the formula, he was happy, and simultaneously noticing the limit of this formula. So there is an example, a famous example. I mean, I try to attempt the Whitehead link. You know how to draw it? Well, I try the Borromean rings. So let me try the Borromean. I have my own way to remember how to draw them. So please just give me some time, and then you understand what I have in mind. Borromean rings are very simple. 3 rings, and then you do one. You decide to start from any you like here, and you start to draw this first circle above this one. So it goes above this here, and under the rest. And then you do the same with the second one, above this one. So above this one, you should do like this. Oh, above, sorry. Okay? And then the third one is, let's say, green, maybe, above this one. So you would go like this and like this. Now you have the Borromean rings. The names come from a family in Milano, near Milano. Name is Borromeo. Borromeo was an important bishop, very influential in Italy. And the family was an influential family in the north of Italy. And they have an island with this symbol in the coat of arms of the family. And this symbol has its own little history, and there is a beautiful paper on that in the, I think, Mathematical Intelligence of many, many years ago by a lady. I don't remember the name. Anyway, these are the rings, and if we put some reference here, say this field, whatever, well, it doesn't matter really. This field and this field, like so the orientation is chosen. So we go to the first one, you see, is minus. With this one, we do the exterior one first, and this is a minus. And then we go here, and this is also a minus. So we have 3 minuses, and then we go inside. And inside we have a plus here, and the plus here, and the plus here. So if we compute the linking number of 1, 2, and 3, 1, 2, and 3, then we get 0. So what's the difference between this and this? Of course, this we cannot disentangle. This is a link. Is a link of 3 components, 3 colors, and we cannot disentangle it. And so there is some problem with this linking number. Linking number, yes, is a measure of topology, but is not enough to capture the topological complexity of certain systems. That, very briefly, is the reason why people started to work on other invariants. Because we have already some invariants, right? We have the number of components is an invariant. 3 in this case, 2 in this case, 1 in this case. Then we have the minimum number of crossings, 0, 0, 1, 2, 3, 4, 5, 6. 6 crossings. So the number of components, the number of crossings, and then we have a linking number, the linking number. Linking number in this case is 0. In that case there are 2 components, 2 crossings, linking number 1. But in this case we have 3 components, 6 crossings, and linking number 0, which sets back the problem. So from there people started to develop other invariants. So the course is a short introduction to, so I cannot go on that, but knots and knots and knots with polynomials. Polynomials are giving you just, don't think of roots of a polynomial. Think of an expression with powers, and this expression is invariant even if you change the knot and you deform it under continuous deformation. So this expression is a topological invariant quantity. And then a different knot, so this knot has a polynomial that cannot be reduced to the polynomial of this knot. So the polynomials are consistent with our search for topological quantities. And the idea is, suppose I get a polynomial that I put all possible information in it. Maybe the polynomial is a little bit sophisticated, is strong enough to tell me whatever is the knot, this is a polynomial of that knot. Not even that. Because of thousands of millions of knots, sometimes the polynomial fails to distinguish 2 different knot types. 2 different knot types come up to have the same polynomial. And so this is the reason why people said, oh, really? I have to look for something else then. But polynomials are pretty powerful. Pretty powerful. And of course encapsulate in some way the information of crossings and linking. Right, I have to stop here. This is just a brief introduction. But I want to say something about helicity now. So I have to prove something about helicity, and I'll do the following. So this is the result we are going to demonstrate. This is fundamental result in topological fluid mechanics, 1969. Is a JFM paper, and is not written the way I write for some reason that I will explain afterwards. In ideal conditions, the helicity HM, we stick to magnetic field, of a magnetic link, let's say B, A, K, of 2 or more components in the shape. I will relax this in a moment, but now I need to say in a shape of planar rings. So like this one. Imagine that this is one ring and this is another ring, and they are linked together inseparably, but we assume that they are planar for some reason. Then we relax this condition of center line, say CI, and tubular boundary, a magnetic surface, so no flux through it. Of flux with and flux phi I. In ideal condition, the helicity is given by HM equal. Remember, we had the definition of helicity: A dot B dV, where this dV is a localized domain, and now we simplify this into thinking that this domain is made by two tubes. Then this helicity is given by I different from J, L phi I, phi J, each flux, multiplied by LK Ij. So I have here a flux phi 1 and a flux phi 2. Okay, this is, of course, I imagine that this is a field by field lines, and of course this is the same. Okay? And they are linked like that, or not. But the helicity is expressed in terms of their linkage. Right, so I have to prove this. So we stick to these two rings, and now what I'll do, I'll just redo the drawing here. So I called the white one was 1. Okay, phi 1. So let me do this. One is this, and the other is this. Okay. So this and this is phi 1, and this is phi 2. And then we consider these two rings of small cross-section. Okay, this will help in the mathematics. So we identified the flux phi 1 with the field B inside, and the flux phi 2 with the field inside the tube. So we have the flux phi 1 equal the integral of AdL of AdL. This flux is constant, so let me write it immediately as a constant. But the phi 1, I can interpret the phi 1 as the circulation of A. Remember, the flux is B through a surface, right? But B, there is a relationship, you know, B, we talked about this, with the vector potential. So I will use this relation with the vector potential to express phi through Stokes as a circulation of A along the axis C2. Okay. So I call this quantity, which is a constant, because it's related to C2, I will call it K2. All right. Now, clearly we have K1 from Stokes' theorem. We apply Stokes' theorem to C1. K1 will be also, this is C1 now, huh? So it will be also A dot L on C1. And this is evidently what we did. If S1 is the cross-section, is just a B nu across the cross-section V2X. All right, S1 being the cross-section here. So we use now the fact that K1 is either 0 or different from 0 if what? If this is plus minus phi 2, K1 is plus minus phi 2 if the two links, if C1 is linked with C2. And is 0 if there is no link, if C1 is not linked with C2. The plus minus depends on the fact that the flux is entering one direction or the other. Okay. Now, K1, we combine the results. K1 related to phi 2 and related to phi 1. K1, if K1 is the result of one passage of phi 2 through it, then is either plus or minus 1. But if we have, if of this phi 2, we have many passages here, we have a number of them. We don't know which number, but you understand. It can be phi 1 or 2 times phi 1 or 3 times phi 1. You know, it's like a solenoid. Like a solenoid, you know, it can go like this, and like this, and like this, and then close out. Okay, so if this is the number, we call it by chance LK12. But we don't know that is a Gauss linking number. We don't know. It's a number. It's a number. Okay, LK12, phi 2. Right. So if we have in general a number of phi 1, a number of links C1, linked with a number of links C2, this can be generalized even further. So we have a chi I equal, this is due to the integral over single curves Ci of A dl, of what? Of a summation, all contribution. So we have on J, LKIJ, going on phi j for a number of components. of axis, C of axis CI. Okay. All right. Now, we can combine the product of phi I and ki in the following way. Now, notice that if suppose we want to construct phi I, chi I. Now, we go to this. Notice that phi I times dl, we assume that these tubes have a small cross-section. So we can approximate this quantity with field B. Phi is the field through the cross-section. Phi is the product of the field through the cross-section. And then we have B times the cross-section to have phi. And the cross-section SI has to be multiplied by dLi. So we get to D3 is a volume, okay? dV is a B D3x. For each I, we have an I here, we have an I there, etc. dLi, etc. Okay, so we are now ready to compute this quantity. So phi I ki is just the integral on each Ci of phi I A dl, and this is the integral on each volume of A dot B d3x on this volume, and this is helicity. Okay, so we got to the helicity. For localized fields. So for localized fields, this is precise. And now we want to find out something about this number that appeared over there. Now, in order to understand that, well, first of all, let me sum over all the tubes. So I should have said here is I, is a single contribution. I sum up on all the tubes, and I have summation over I of the integral Vi A dot B d3x, and this is just a summation over the phi I ki, and this is just summation because we have an lk there, lki j, I different from j over the whole stuff, phi I, phi j. Okay, so I said that we have this number, we don't know what number it is, and we want to find it out. And in order to find it out, we have to we have to use the relationship between A and B. Now, A and B is like U and omega. One is induced by the other. Which one is inducing is B. And what is inducing a potential, right? So we have to find out this induction. And this induction law, we saw it already, is Biot-Savart. So we have in general A, due to Biot-Savart, and this A is 1 over 4 pi integral of B x star. I have to say that I suspect while I'm writing this, I know that this is correct. But I have a sense, it's probably, I don't have it with me now, but in the notes, if you go to the Biot-Savart law, actually I do have all the notes with me. Probably the number are but probably the Biot-Savart law for vorticity is a minus somewhere that doesn't click with what I'm writing. I don't know if you go to chapter 1.78, there is a minus to correct there, I think, because we have to start with the field, or at least this is the way I remember it. X minus X star, or let's okay. Yes, sure. I was just paused by I was just thinking, what is this X star? The X star is the position vector. Oops, is the position vector on the inducing. You know, B depends on X star because X star is the point, is the source point. Okay, so this is the source point. So is D3X star. So this is Biot-Savart. Biot-Savart. Induction law. And when I wrote the induction law for vorticity, I'm pretty sure that I made a mistake. There is on the notes. It shouldn't be the minus that you have, because that's the way I remember it. Anyway, you can check. Okay, so this is the induction from B, and we have to take this and to put it in there, here. That's it. So we have to put it there. So you see, if we have fields that are localized, we can always take these phi dl as the field times the volume. So if we do that, we get the following. Now, I forgot to say that in general, since B is defined in terms of the vector potential A, we may think of A in general given by A of Biot-Savart plus some contribution of a gauge, so grad phi, let me call it like this, little phi. And we can see that if we substitute this, if we substitute in this expression, in this one, the integral over V of grad phi, of grad little phi B d3x, this is integral on V of the divergence of little phi B d3x. This is because, remember, B is divergence-less. We use the condition if B equals 0. And this is integral on, we use divergence theorem again, and this is the flux phi B through the surface, nu on d2 on d2x. But we assume that there is no flux B nu is no flux through the surface because the bounding surface is a magnetic surface. So whatever is the gauge here that we are not happy with or happy with, it doesn't affect the final result. And the final result is that HM is 1 over 4 pi integral of VI integral on Vj of xi minus xj. I'm going back to indices, x1 and x2 denoting C1 and C2. And if I'm generalizing this to a number of these flux tubes linked to one another, then I have Bxi wedge B xj divided by xi minus xj mod 3 d3xi d3xj. And, okay, so this is indeed the sum of I different from j of L, K, I, j, phi j, in another sense, in the sense that where L, K, I, j is indeed the Gauss linking number. So we established the connection between helicity of two, for the moment, let's say, planar rings that are linked together. And then many more, n planar rings altogether, or n combination of planar rings. Now, of course, we are not happy because we want to say something even more general. What about if, because the relationship is with linking number, we can now relax the fact that there are planar rings, we can deform them. There is no information about geometry here, so they can be not rigid, planar ring, but deformable, but still not happy because we may have knots. What about knots and the very complicated links? Okay, so this is more or less time to stop. Yes?
Sorry.
Yeah.
Is that formula the denominator should be
Oh, a 3 here. Thank you. Yeah. Sorry. Yeah, it's a 3, of course. It's a 3 because it's Biot-Savart. Sorry. Okay, so we come to a close of this course, and I cannot stop without going to knots and links. So I have to consider those. But to give you a proof of what I'm stating is impossible. Not even if I want to say something else, then I better use my time for something else than to give you the proof of this. But this is a piece of work I did with Keith some time ago now. It's a joke. Long time ago. So we have a result, the following. Let me introduce first. I need to go back before talking about that. I need to go back to the idea of a flux tube with a twist, because this is central in what I'm going to say. So I'll first duel on another quantity that is topologically invariant, and is the following. So Tate noticed that in his first publication, in his first paper, he noticed that this linking number is great. But what about if I consider one knot? So a trefoil knot. Trefoil knot, I'm now trying my best again. Sometimes I'm lucky and sometimes I'm not lucky. Sometimes I get the trefoil knot instantly, sometimes I look it and then I look it. So this is a trefoil knot, and he says, yes, that's wonderful, it's a linking number. It measured linkage. But what about knots? Do we have a way to measure linkage of knots? And he was very close to find what I'm going to tell you, because it's written there. At a certain point he says, well, I can think of a physical knot, and the physical knot, when we draw physical knots, we put tubes, and if we put tube, we put a second curve, and just to denote the fact that this is some thickness there. And then he says, well, I can consider, I don't know about the linking of a knot, it doesn't make sense, terminologically, semantically. The linking with what? Is one structure only. But if I think of some thickness, and this thickness being represented by these two curves, then I can think of the linking between one and the other. So I can do this in a say, mathematical way may be in thinking that these two curves are collapsing on one curve. So, okay, so I make the tube thin and thin and thin until I get almost a line. It's not a line, it's never a line. I need two curves. But it's almost like a space curve. Okay, so what can be done is the following. So we can construct a ribbon. And the ribbon is what I already drew. A center line, or let me draw the center line in red, is probably better. So we have a center line here, one curve. This is C1. And then I have a second curve, this one, that goes like this. And I construct this as a ribbon. And the idea is that maybe by using this ribbon model, I can come up with some information on topology. The topology of this ribbon. And we already said that this unit quantity is n. We already said that this is C1, this is C2. We already said something. For example, that there is a twist that we can introduce, etc., etc., etc. He didn't go farther. So he stopped there and he started to do measurements. Very interesting. Measurements. He constructed, he produced knots with a piece of copper, and he made the current flowing, and he measured at the time was called the power, the electric power, or some work that was done by the current. And then he reported at the Royal Society his failure to measure knottedness by electromagnetic means, which is amazing statement. 1880, 1870. Amazing. Let's see how to get something out of linking number. So years passed, and arrived a mathematician, a geometer from Romania, who did this work. I cannot produce the work here because it's 40 pages of mathematics, but the idea can be discussed quickly. We have one curve and the second curve linking with the first. So this is C1, and this is okay, whatever you like. You like it C2, maybe C2 and C1. I should have, okay, it doesn't matter. I wanted to reverse the colors, but too late now. And you keep fixed C2. It's not the way it's done the work, but follow the concept. And now you modify this second curve. I'm sorry, I'm mixing up the symbols, but you understand what I want to say. So to be very close to C1. So we didn't modify topology. Geometry changes, but topology is the same. And now we construct. We stop there and we think of the second curve, or the other way around, constructed from the first. So we put together a ribbon, and we do this. And this is exactly what Calugarianu did. So we have a theorem here. So the ribbon, I repeat very, very quickly, a ribbon between two curves, C1 and C2, is just defined as the sum of, let's say, given one curve, x1, for C1 in terms of x1s, we can construct a second curve, x2, as x1 function of s plus a measure, epsilon, finite, along n being the normal, unit normal. And then we do something else. Now we start thinking that this ribbon is the same object, so the second curve, C2, is actually the first plus something, plus some twisted. So we start thinking to drop this and to call the second curve C star, right, C star. And so it's only one thing, and then we have an X, and the same here is an X and an X star. I use X and X star in Biot-Savart, in the previous expression. We start thinking that these two curves are belonging, or one in the middle here, and another in the middle here, etc., to the same structure. But they are still separated by a finite epsilon. And now we can compute the linking number, Lk, between what? Between one curve and the other, between C and C star. Okay? C and C star mathematically are separated, and this is well defined. And then what we do what you learn to do so many times in school, limit for epsilon going to 0 of this quantity. And you call this quantity self-linking, and the theorem goes like this, famous important theorem by Kaluga-Reanu, 1961, is the following. First of all, SL, self-linking number, is a topological invariant of the ribbon. And moreover, it admits the following decomposition, which is one of the rarest things in the whole mathematics. A topological quantity that connects global geometric quantities, writhe and twist, where WR, I should stress, because it's important to stress it when you introduce concepts, writhe depends on C only, and twist depends on C and C star. Through the ribbon concept, where writhe is writhe and twist. Oh, sorry, I didn't write it. Better to write it. Is the writhing of C and twist C star is the total twist number of the ribbon R, C star. Now, there is a mathematical expression for the writhe and for the twist. For the twist, you saw it already. For the writhe, I write it immediately. And what this theorem says that it's like, you know, for water, when you do, you have the total amount of water that can exchange between two containers, and they are connected, and it's the same thing. The total amount of information, you call it SL, but this SL, this self-linkage, can be either a lot of writhe, a very low twist, or a lot of twist and very low writhe. I come to explain that in a minute. I just like to give you the expression for the writhe of C. So the writhe is a geometric quantity, where is the writhing number of C and twist is the twist number of C. Writhe a global geometric quantity of C given by 1 over 4 pi, believe it or not. Double integral is exactly the linking number, with one exception, that this is on C only. It depends only on one curve. That's why it's a geometric property of the given curve of C. And you have what? You have x1 minus x2. Okay, no, sorry. I used x and x star. X minus x star dx wedge dx star. X minus x star to the cube is exactly, now I can say it, is exactly BO sub r. It's BO sub r that play the role in helicity, in finding helicity in terms of linking number, with one exception, that in that case was a linking number, was really BO sub r, because these were two distinct curves. But here is the same curve. Same curve. And twist of CC star is a global geometric quantity of the ribbon and is given by it can be further decomposed. We saw it as 1 over 2 pi integral of total torsion ds of C. So this quantity T, total torsion T, depends only on one curve, say the center of the tube axis, and there is another one here that depends really on this is intrinsic twist, and this depends on the winding of the second curve C star with respect to the first. Okay? Remember the case of the straight ribbon. If it is a straight ribbon, there is no torsion of the axis C, but you still have a rotation of this quantity n around it, and so you contribute with this term here. So this is called curly n, and so we have T of C plus curly n of CC star. Now we can finally express the result of helicity for knotted tubes. And linked tubes. We can generalize the result of Keith 69. Okay, as I said, derivation is a bit long and a bit convoluted. So this is the work we did together. And is the following in ideal condition. The helicity HM of a magnetic knot B, K, centered. Okay, I dropped this. Centered on the knot with tubular boundary, a magnetic surface, surface and flux phi is given by HM equal self-linking number times the flux phi squared. So in general, we can put these results together as a corollary of everything. What about a system of knots and links together of any shape? Then we can put the helicity of each single contribution with the helicity of the mutual. So as a corollary, we have the following H for a system of essential topology. We have H integral A dot B dV is equal to sum over I of phi I SL plus some I different from J, otherwise there is a 2 there, phi I, phi J, LKIJ. That's it. Now, the benefit of this formula and the benefit of topological interpretation of this formula is great, because we can, instead of measuring A and B in a system, which is a lot of information, remember one of them is Biot-Savart, and then we have to integrate over the domain of B. Imagine a system that is fluid and is moving, etc. I think it's much better, first of all, to evaluate the flux tube if the field is localized. And I will show you at least one picture of plasma loops. And if we have time, and if you like to spend a little bit more time, I have a couple of movies. One I download, are available, okay, are publicly available. There are beautiful movies from NASA and from other missions, Inode, the Japanese mission, and other missions, TRACE, European missions, etc. So these localized fields are very localized. And so the flux can be measured rather easily, estimated rather easily. Now, what about this measure, linking and self-linking? Well, linking number is definitely not so difficult, because you take projection of an event, any projection, a picture. You take a picture of an event, and then by image analysis, you count, you count the crossing, overcrossing, undercrossing. That is done in astrophysics, not so much. Not so much. I talked about this maybe 15 years ago in Boulder, telling them, they have data every single second of the sun. They should compute these things. It's easy to compute them, but everyone is busy, so at the moment, I don't know. They are doing this, some groups. But in biology, they were very quick to pick it up. And so now it's a standard technique. They take one picture of a biological, of DNA sedimenting, whatever it is, the shape, and they do data analysis on that, and they classify knots and links. And they estimate this linking number through that. And self-linking, same thing. Self-linking is a geometric measure. Now, I have no time to show you this, but, the same analysis as I did, or as I mentioned it for the Gauss linking number, can be done on the right. We can interpret the crossings on the right. Remember, this is dependent on the projection, is not a topological quantity, but similarly, we can come up with the same type of formula. Epsilon r being the signs of the crossings, and we can estimate this, and if we take an average estimate of that, then we come up with the analytical right. So you do several pictures, 3, 4 satellites of the same event are sufficient to give you an approximate estimate of the exact rising number. As you increase the number of pictures of the same event, this estimate is getting better and better, gets better and better. You can control the error. Now what you have here from pictures, well, total torsion. Total torsion is not so difficult to compute, is numerically difficult to compute, but is not so difficult given a picture, 2 or 3 pictures of the same event in space, but total torsion is always pretty low. And this is the difficult one, twist. But for magnetic, for solar loops, twist can be estimated by observation on measurements on photospheric motion. And they transfer twist in the loops. And of course, this is a critical quantity for energy considerations. And for other aspects, is also the critical quantity for a number of us to pay attention on. So twist, let's say that for physical application, twist is important, more than maybe all the rest. But it's because we did all this progress that we can say this. Now we focus on internal structures, and we go finer and finer in the analysis. When Keith came out with this result, was considered of no importance, maybe. Many years passed, and gradually got importance, especially through measurements relatively to energy of the phenomena, and then now we are going to look inside the structures and have more information.